Today in physics, we'll be talking about a model of the Atwood machine under the effects of friction. This is part 4. Here's our model of the Atwood machine, where we have a fixed cylinder, it's unable to move, and we have a massless string that's wound over the cylinder. Now, the coefficient of friction, static friction, between the cylinder and the string is 1.0, and we have two masses. Now we're asked how many times, at least, do we need to wind the string around the cylinder in order to keep the two masses at rest? We're going to define the number of turns as 0 when the string is only laid over the cylinder as such, and friction will only act between the string and the cylinder, but it won't act between the two parts of the string that are in contact when we're winding it more than 0 turns. We're also given some helpful approximations when we have some number x and it's much smaller than 1. We're given the approximation that cosine of x is approximately 1, sine of x is approximately x, 1 over 1 minus x is approximately 1 plus x. And we're also given the fact that when h goes to infinity, 1 plus 1 over h to the h power approaches e, also known as 2.718, and so on. Previously, in part 3, we figured out for a 2n-sided prism, for our model of the Atwood machine, there is a relationship between small m and large m, where small m is the minimum amount of mass that is required to keep the system at rest. So the relationship we found was that small m is equal to large M times this coefficient, cosine of alpha minus mu0 sine of alpha over cosine of alpha plus mu0 sine of alpha, and this is raised to the nth power. We also define alpha to be pi over 2n, where 2n is the total number of sides. Now the question is, how can we relate the 2n-sided prism to a circle? So here we have a square, so n equals 2, since remember we're saying the number of sides is 2n, so the number of sides for a square is 4, for a hexagon n is 3, 6, then 4, and 8, and so on and so on. But what we can see, when we add more sides to a regular polygon or an equilateral polygon, it seems to approach the shape of a circle. So when n approaches infinity, our 2n-sided polygon also approaches infinity for its number of sides. And if we think about it, a circle doesn't really have any sides, or we could say it has infinitely many sides. So our 2n-sided polygon then approaches a circle. Now we have our relationship between the two masses from before for our 2n-sided prism. And now we've shown that when n goes to infinity, this can be applied to a circle. Now that also changes what alpha becomes, since alpha, we wrote, is pi over 2n. And when n goes to infinity, anything that has the form 1 over n, so alpha definitely fits that as pi over 2n, that's going to approach 0. So alpha is going to approach 0. Or in other words, it's going to be much smaller than 1. Much smaller than 1. That for alpha approaching 0 is that pi over 2, we can also write alpha as being to pi over 2, divide that by n. And pi over 2 always stays the same, so it's a finite number. But as n gets larger and larger, and it's on the denominator, so the whole fraction will get smaller and smaller until it pretty much approaches 0. So it's much smaller than 1. Now that we've established that, we can look back to some of the helpful tips that were given to us at the beginning. So we see that alpha perfectly fits for the requirement for x, namely it's much smaller than 1. And so then cosine of alpha becomes approximately 1, and sine of alpha becomes approximately x. So we can rewrite our equation as small m is equal to large m times cosine of alpha, that becomes 1, minus mu 0 times sine of alpha. So mu 0 times sine of alpha becomes alpha over 1 plus mu 0 of alpha. And we have this raised to the nth power. Now we can also use one of our other helpful hints, namely 1 over 1 minus x is approximately equal to 1 plus x when x is much, much smaller than 1. And if we look at our coefficient though, it seems to be flipped, so we can simply solve this equation for large m. So we get small m times the coefficient of 1 plus mu 0 alpha over 1 minus mu 0 alpha to the nth power, and this equals large m. Now we can rewrite this coefficient to be 1 over 1 minus mu 0 alpha plus mu 0 alpha over 1 minus mu 0 alpha to the nth power, and this equals large m. Now when we write it in this form, we can see that we can replace 1 over 1 minus mu 0 times alpha. And since we know that mu 0 times alpha is a small number, we have that become approximately 1 plus mu 0 alpha plus mu 0 alpha over 1 minus mu 0 alpha. So this equals large m. Similarly, we can also write the second term in the coefficient as plus 1 plus mu 0 times alpha times mu 0 times alpha. Now, when we multiply the second term out, we find that this is mu 0 alpha plus mu 0 squared alpha squared. But mu 0 squared alpha squared is going to be much, much closer to 0 than alpha itself when n is approaching infinity. So we can pretty much ignore that term since it's pretty much negligible. So we raise this to the nth power, and this equals m. Now, we can also write this again by plugging in what we know alpha to be, namely, this is m1 plus 2 times mu 0, and alpha is equal to pi over 2n. When raise this to the n power, we have this equal to large m. So small m times 1 plus mu 0 pi over n raised to the nth power is equal to large m. So now we have large m is equal to small m times 1 plus mu 0 pi over n raised to the nth power. And we know that n is approaching infinity. Now we were also given the fact that when we have some number h, and h is going to infinity, the expression 1 plus 1 over h to the h power approaches e. Now we can look at our expression for a coefficient and see that it somewhat resembles a possible 1 plus 1 over h to the h power. So one way we can achieve that is saying, let's say h is equal to n over mu 0 pi. Then we can say m is equal to small m times 1 plus 1 over h to the h times mu 0 pi power. So when we have h times mu 0 pi, the mu 0 pi cancels out with the mu 0 pi in the h's denominator, so we find that equals n. And when we have 1 over h, then we have 1 over n over mu 0 pi. So we can simplify that to mu 0 pi over n, which also works out. So once this happens, now all we need to do is show that h does go to infinity, the way we've defined it. We know that n goes to infinity, and we're dividing n by a finite number, namely mu 0 times pi. Mu 0 times pi never gets bigger, never gets smaller, it always stays the same, but n always gets larger and larger. So we can also conclude that h will also approach infinity. Then we can replace our expression for large m and small m to be large m is equal to small m times e to the mu 0 pi's power. And one way we can see that this is e to the mu 0 pi's power is that if we have these brackets, we have 1 plus 1 over h to the hth power, when we raise that to the mu0 pith power, it's equivalent to multiplying the hth power by mu0 pi. So we conclude that large M is equal to small m times e to the mu0 pi. So we've come a lot way closer. We can also write this as small m is equal to large M times e to the negative mu0 pi, since we're just dividing by e to the mu0 pi on both sides. However, keep in mind this is not our end goal, because we're asked to find how many times do we need to wind the string. We're already given m, and we're already given the large M, but now we need to find a way to see how winding the string around the cylinder will help support a larger weight even when the minimum weight needed when there's no turns is not there. So we're solving for the number of turns that we need to wind the string. So let's call that number n. So n is the number of times needed to wind the string. Wind the string around our cylinder. So when the string is simply laid over the cylinder, so namely when n equals 0, then our required mass in order for the system to remain at balance is expressed by this equation. But when n equals some number that isn't 0, so 1, 2, 3, and so on, then what we get is that the more times we wind the string around the cylinder, the more friction there is between the string and the cylinder, because there's more string that is on the cylinder that allows for more friction, since friction is a contact force. So when n equals some number like 1, 2, 3, 4, so on, we have to multiply this coefficient, e to the negative mu0 pi, more times. So every time we wrap it around the cylinder, we have to multiply e twice. So when n equals 1, for example, when n equals 0, we have just this amount of friction. And this amount of friction is expressed by e to the mu0 pi. But when n equals 1, we find that this is when n equals 0, and then when n equals 1, we have another time, as well as another loop around the top. And I'm drawing it to seem as if the top string is laying above the other strings, but this is a cylinder, so it's all on the same level, but this is just so we can see what's happening. So this is from when n equals 0. So we know that e mu0 pi. But we also have another time and another time. So we have to multiply by 2 more of this coefficient. So we find that the coefficient then becomes e to the negative 3 times mu0 pi. So in other words, the more times we wrap the string around the cylinder, the smaller small n can be. The smaller small n can be. Because since this is negative, that means it's m over e to the 3rd mu0 pi power. So the more times we wind the string around, the larger this number becomes, so the larger the denominator becomes, and the smaller small m has to be in order to keep the system at rest. We also want a more general equation for how this works. When n equals 0, we know that this coefficient has to be there. So it makes sense to say that when n equals 0, we have to add 1 to some n. But another thing is that each time we wind the string around the cylinder, we wrap it over the top and the bottom. So we wrap it over both halves of the cylinder. So it makes sense to multiply n by 2. So we find that our coefficient looks like this. Once we multiply by large M, we could say this equals small m. So this is our much more general equation for the relationship between the two masses required to keep the system at rest when we have a certain number of times in which the string is wrapped around the cylinder. In this case, we've been given what small m and large m are, so now we need to solve for n. Now let's solve for n. we can divide by large M on both sides to get this. Now if we take the natural log of both sides, we get this new equation, and we can conclude that n is equal to -1/2 mu 0 pi, the natural log of small m over large M minus 1. Now, the natural log of small m over large M is already going to be negative, so we can also write n as being this, 1/2 mu 0 pi times the natural log of large M over small m minus 1. And if we put in our values, knowing that mu 0 is also equal to 1.0, we find that n is approximately 0.88. So since n is going to be an integer, we require that at minimum, in order for the system to be at rest, we need n to be 1. So we need to wrap the string at least once around the cylinder. And this is our result.